Ever look at like I don't know, a pencil and wonder what's really going on inside? Like at the tiniest
Yeah,
level.
yeah.
We're going deep today into the atomic nucleus, that tiny powerhouse at the heart of every atom.
And it's a lot more exciting than it might sound. We're talking forces so strong they hold particles together against all odds, and reactions that release energy, well, on a scale that's hard to even imagine.
Okay, so before we get to the mind-blowing reactions, let's start with the basics. What's actually inside the nucleus?
Well, you've got your protons
Right,
and your neutrons,
right.
collectively called nucleons. Protons, the positively charged guys, give an atom its identity, determine what element it is. But neutrons, well, they're a bit more enigmatic.
Right. I remember from school that protons determine the element, thanks to the periodic table and all that.
Yeah.
But what's so special about neutrons? They seem kind of quiet.
They are until they're not. Inside the nucleus, protons and neutrons hang out. Stable,
Okay.
happy. But a neutron on its own,
Okay.
outside the nucleus, that's a different story. It's unstable and actually decays.
Wait, decays, like it just disappears.
Not quite. It transforms. A free neutron decays into a proton, an electron, and a tiny particle called an antineutrino, and the whole process happens pretty quickly,
Okay.
with a half-life of only about 12 minutes.
Whoa, so a neutron basically has an expiration date if it's not hanging out with its proton pals in the nucleus.
Right.
That's wild. But how do scientists even keep track of all these particles inside the nucleus? It seems like a chaotic jumble.
Actually, there's a really elegant system for that.
Okay.
Think back to the periodic table and the atomic number of an element.
Yeah.
That number represents the number of protons in an atom's nucleus, which we call the charge number, symbolized by the letter Z. So the charge number is like the proton ID card for each element.
So that's how we know we're dealing with oxygen or gold or any other element. But what about the neutrons? How do we factor those in?
That's where the mass number comes in, denoted by the letter A. It represents the total number of protons and neutrons in the nucleus. It's like a census for the entire nuclear population.
Okay, so charge number Z tells us the number of protons, and mass number A tells us the total number of protons and neutrons. Got it. I remember seeing those symbols in chemistry class, like euro for oxygen. That's how scientists denote different isotopes, right?
Exactly. That notation tells us everything we need to know about the nuclear makeup of that particular oxygen atom. In this case, it has 8 protons and 8 neutrons, giving it a mass number of 16.
This is starting to make a lot more sense. But here's a question that's bugging me. If the nucleus is packed with all these particles, shouldn't it be pretty big?
That's where things get really interesting. The nucleus is surprisingly tiny.
Okay.
To give you an idea of the scale, if an atom were the size of a football stadium, the nucleus would be like a tiny marble sitting right at the center.
Wait, seriously. That's mind-blowing.
Yeah.
I always pictured the atom as this neatly arranged structure. With the nucleus taking up a decent amount of space, it's incredible to think there's so much empty space in an atom.
Yeah.
It's like a vast cosmic cathedral with a tiny, dense altar at its center.
That's a great analogy. And here's the even crazier part. Almost all of the atom's mass is concentrated in that tiny nucleus. We're talking incredible density here.
Okay, now I'm really curious. If the nucleus is so tiny and packed with all these positively charged protons, why don't they just repel each other and fly apart? What's holding them together in such a small space?
That's the power of the strong nuclear force.
Yeah.
It's one of the fundamental forces of nature.
Yeah.
And it acts over very short distances,
Yeah.
binding those nucleons together with unimaginable strength. It's like an incredibly strong glue that overrides the electromagnetic repulsion between the protons.
So it's this incredible force that's responsible for holding the very fabric of matter together.
Yeah.
That's amazing. But how does this force relate to all that energy we were talking about earlier?
That's where Einstein's famous equation emis work comes into play. Remember, energy and mass are two sides of the same coin.
Of course, it's practically a pop culture icon at this point.
Mhm.
But I'm still a bit fuzzy on how mass actually becomes energy in the nucleus.
It all comes down to binding energy,
Ah.
the energy that holds the nucleus together. When protons and neutrons join forces to form a nucleus, they actually release some of their mass as energy. The difference in mass between the individual nucleons and the combined nucleus is called the mass defect. And it's this mass that's converted into energy.
So it's like they're giving up a little piece of themselves to forge this powerful bond.
Exactly. And the more tightly bound the nucleus is, the more stable it is. Iron, for example, has an incredibly high binding energy per nucleon, making it one of the most stable elements in the universe.
Mm.
That's why it's so abundant.
Wow, so the binding energy is like a measure of how much the nucleons want to stick together.
Right.
It's fascinating how this tiny nucleus is governed by these incredible forces and energy transformations. But what happens when this binding energy is disturbed? What if something, crashes into the nucleus?
Well, then we enter the realm of nuclear reactions.
Yep.
These are events where particles collide with nuclei and things can get pretty dramatic.
Okay, now I'm really intrigued. Tell me more about these nuclear reactions.
Imagine a cosmic billiards game, but with particles smashing into nuclei at incredibly high speeds. These collisions can release a tremendous amount of energy and even transform elements from one to another.
Sounds like there's a lot going on in these reactions. How do scientists even keep track of all the chaos? Do they have a special scorecard or something?
They do. They use a special notation system to describe these collisions. For example, a reaction might be written as XABY, where X represents the target nucleus, A is the incoming particle, B is the ejected particle, and Y is the resulting nucleus. It's like a before and after snapshot of the collision.
So it's a way of capturing the whole sequence of events in a neat little equation. But with all this energy and particle rearranging, are there any rules that govern these nuclear reactions? It seems like anything goes.
Actually, there are some fundamental laws that always apply. We have the conservation of momentum, ensuring that the total momentum of the system before and after the reaction stays the same. Then there's the conservation of charge, which means the total charge must always balance out.
So it's not complete anarchy in there. There's still a sense of order
Yeah.
amidst the chaos.
Absolutely. And then we have the big one, the conservation of mass energy.
Got it?
This law takes into account Einstein's famous equation and ensures that the total mass energy of the system remains constant throughout the reaction.
So even in these dramatic nuclear events, there's an underlying balance at play.
Right.
That's pretty reassuring. But I'm guessing there are different types of nuclear reactions, right?
You're right. The two major types are
Okay.
fission and fusion. They're like two sides of the same coin, both involving incredible amounts of energy, but in very different ways.
Okay, I'm ready for this nuclear showdown. Fission versus fusion. Let's break it down. What's the difference?
Think of fission as splitting wood
Okay.
and fusion as igniting a star. In fission, a heavy nucleus, like uranium, is split into lighter nuclei, releasing a tremendous amount of energy.
Oh, like in nuclear power plants and atomic bombs.
Yeah.
That's fission, right?
Exactly. In a nuclear reactor, we control the fission process to harness the released energy for power generation. But in an atomic bomb, it's an uncontrolled chain reaction, resulting in a devastating explosion.
Wow, so fission is incredibly powerful, but it sounds like a double-edged sword.
Hmm.
Controlling those chain reactions must be incredibly challenging and risky. What about fusion? Is that the process that powers the sun?
You bet. Fusion is the ultimate power source of stars, combining light nuclei like hydrogen to form a heavier nucleus like helium. And in the process, it releases even more energy than fission.
That's incredible. It's amazing to think that the same process that makes stars shine is happening right here on Earth in labs and research facilities.
Right. We're trying to replicate the conditions of the sun's core, where fusion occurs naturally. It requires extremely high temperatures and pressures, which is a huge scientific and engineering challenge. But the potential payoff is enormous. Clean, virtually limitless energy.
It sounds like fusion is the holy grail of energy production. It's amazing how we can learn so much about the universe by studying something as tiny as the atomic nucleus.
And we've only just begun to scratch the surface. There's still so much we don't know.
Right.
For example, we've talked about the energy released in these reactions.
Yeah.
But have you ever considered where that energy actually comes from?
That's a really good question. We've talked about the binding energy and the conversion of mass into energy. But the sheer amount of energy released in nuclear reactions is mind-boggling. It seems to defy our everyday experience with energy.
Yeah.
Where does that raw power actually originate?
That's a question that has puzzled scientists for a long time. It gets to the heart of some of the most fundamental mysteries of the universe. The nature of mass, the nature of energy, and how they're intertwined at the most basic level.
It's amazing to think that something as seemingly simple as a nucleus can hold such profound secrets.
It is. And speaking of secrets, there's another fascinating aspect of the nucleus we haven't touched on yet.
Okay.
Radioactivity.
Ooh, radioactivity. That's the stuff of sci-fi movies and superhero origin stories. But seriously, what exactly is radioactivity?
It's all about unstable nuclei,
Ugh.
those that are just too energetic to stay put.
Right.
Think of them as cosmic pressure valves, releasing energy and particles in a spontaneous dance of decay.
So it's like the nucleus is trying to shed some energy to become more stable.
Exactly. And this dance of decay comes in three main types: alpha decay, beta decay, and gamma decay. Each one involves the nucleus releasing energy and/or particles in a unique way.
Okay, I'm ready to learn the moves. Let's start with alpha decay. What's happening there?
Imagine the nucleus spitting out a tiny, positively charged bullet.
Okay.
That's alpha decay. It involves the emission of an alpha particle, which is essentially a helium nucleus. 2 protons and 2 neutrons bundled together.
So it's like the nucleus is shedding a little bit of itself to become more stable. Does this change what element it is?
It does. When a nucleus undergoes alpha decay, its atomic number decreases by 2 because it's lost 2 protons, and its mass number decreases by 4 because it's lost 2 protons and 2 neutrons. So the element actually transforms into a different one.
Wow, that's incredible. It's like nuclear alchemy, transforming one element into another. What about beta decay? What's going on there?
Beta decay is a bit more subtle. It's like a neutron decides to switch teams, transforming into a proton within the nucleus.
Wait, a neutron can just become a proton? How does that even happen?
It's all thanks to the weak nuclear force,
Okay.
another fundamental force of nature. It governs certain types of particle decay, and it's what allows a neutron to morph into a proton during beta decay. In the process, the nucleus emits an electron, called a beta particle, and an antineutrino.
Okay, so in beta decay, the nucleus gains a proton and loses a neutron. Does that change the mass number?
Actually, no. The mass number stays the same because even though the composition changes, the total number of nucleons remains the same. However, the atomic number increases by 1 because we've gained a proton, so the element transforms again.
So alpha decay is like tossing something out the window, and beta decay is like rearranging the furniture inside. What about gamma decay? Does it involve particles too?
Gamma decay is a bit different. It's not about changing the composition of the nucleus.
Okay.
Instead, it's about releasing pure energy in the form of a gamma ray, a high-energy photon.
So no particles flying out this time, just a burst of energy.
Exactly. Think of it like the nucleus taking a deep breath and letting out a sigh of relief. It helps the nucleus transition from a high-energy state to a lower, more stable energy state.
So gamma decay is like the nucleus's way of calming down after all the excitement of alpha and beta decay. It's fascinating how these processes work together to create a sort of balance within the nucleus.
You've got it. And these decay processes are governed by some pretty strict rules.
Okay.
One of the most important is the concept of half-life.
Half-life. Is that like the expiration date for radioactive nuclei?
It's similar. Half-life is the time it takes for half of the radioactive nuclei in a sample to decay. So if you start with, say, 100 radioactive nuclei and the half-life is 10 minutes, after 10 minutes you'd have 50 left, and after another 10 minutes only 25, and so on.
It's like a nuclear countdown clock.
Yeah,
Each radioactive isotope has its own unique half-life, right?
precisely. And these half-lives can range from fractions of a second to billions of years. Understanding half-lives is crucial for a wide range of applications.
Yeah.
From radiometric dating to medical treatments.
Okay, so by analyzing the decay products and knowing the half-lives, scientists can figure out the age of ancient artifacts or target specific cells in the body for treatment.
Exactly. It's all about harnessing the power of radioactivity for scientific and medical advancements.
This is all so incredibly fascinating. It's amazing to think that these processes happening at such a tiny scale have such profound implications for our understanding of the universe and our ability to use this knowledge for practical applications.
It really highlights the interconnectedness of everything, from the smallest particles to the vastness of the cosmos.
Right.
And speaking of the bigger picture, it's important to remember that radioactivity is a natural phenomenon that's been happening since the beginning of the universe. It's not something we created in a lab.
Right. So all those radioactive elements we hear about, like uranium and plutonium, they weren't just cooked up by scientists. They occur naturally.
Absolutely. They're a product of stellar processes, formed in the hearts of stars. Radioactivity is a constant reminder of the dynamic nature of matter, constantly changing and transforming at the most fundamental levels. It's a process that has shaped the universe as we know it, from the creation of elements to the decay of isotopes that provide us with clues about the Earth's history and beyond.
It's awe-inspiring to think that something as tiny as the atomic nucleus can hold so much power, history, and potential. We've gone from protons and neutrons to fission, fusion, and now radioactive decay. It's been an incredible journey into the heart of matter.
And we've only just scratched the surface. There's still so much more to explore and discover about the atomic nucleus. But for now, let's take a moment to appreciate just how much we've learned about this tiny yet mighty realm of the universe.
I agree. It's been a truly mind-expanding deep dive. But before we wrap up, I have one last question that's been bugging me. We've talked about the different types of radioactive decay, but what triggers them in the first place? What makes a nucleus decide it's time to shed some energy or particles? It's like there's some internal clock ticking away inside the nucleus, and when the alarm goes off, it's decay time.
Yeah.
But what sets that clock?
That's a great question. And it gets to the heart of what makes a nucleus stable or unstable. You see, it all comes down to the balance of forces within the nucleus.
Okay.
We've talked about the strong nuclear force, that incredible glue that holds the nucleons together. But there's also the electromagnetic force at play with those positively charged protons repelling each other.
Right. It's like a constant tug of war happening inside the nucleus.
Exactly. And the stability of a nucleus depends on whether those forces are balanced. If the strong force is dominant, the nucleus is happy and stable. But if the electromagnetic repulsion starts to win out, well, that's when things get interesting.
So it's all about finding that sweet spot where the forces are in equilibrium.
Precisely. And there are a few factors that can tip the scales towards instability. One is the size of the nucleus.
Okay.
As the nucleus gets larger, the strong force, which acts over very short distances, starts to have trouble keeping all those protons in check.
Ah, so it's like trying to herd a growing crowd of cats. The bigger the crowd, the harder it is to keep them all together.
That's a great analogy. And then there's the neutron-to-proton ratio.
Okay.
Neutrons, being neutral, help to dilute the electromagnetic repulsion between the protons. They act like little peacemakers, keeping the protons from getting too close and pushing each other away.
So it's like having a buffer zone between the feisty protons.
Exactly. But there's an ideal neutron-to-proton ratio for each element. If the ratio is off either too many neutrons or too few, the nucleus becomes unstable and prone to decay.
Okay, so it's all about maintaining that delicate balance between the forces, the size of the nucleus, and the neutron-to-proton ratio. If anything throws those factors off, the nucleus goes into decay mode to try and restore equilibrium.
You've got it. And it's through these decay processes that radioactive nuclei eventually transform into more stable forms, releasing energy and particles along the way. It's a constant dance of transformation and energy release that's been happening since the dawn of time.
It's mind-blowing to think about all the activity happening within something as tiny as the atomic nucleus. It's like a whole universe unto itself, governed by these incredible forces and laws of physics.
And it's a reminder that even in the seemingly mundane, there are profound secrets waiting to be uncovered. Every time we look deeper into the world around us, we discover new layers of complexity and beauty.
Well said. It's been an amazing journey into the heart of matter. We've explored the particles, the forces, the reactions, and the decay processes that shape the atomic nucleus, and ultimately the world as we know it.
And who knows what other mysteries await us in this tiny yet powerful realm? There's always more to learn, more to discover, and more to wonder about.
Absolutely. So until next time, keep exploring, keep asking questions, and keep diving deep into the wonders of the universe. Even in the seemingly ordinary situation, you never know what incredible insights you might uncover.